Okay, so I'm finishing up the last two, 5 and 6 from this ditto, and I left off in my afternoon class talked to sulfate. I know my first period class, my first honors class, we talked about the sulfate ion a little more in detail. So I want to add a few things, finish these, and you can continue on. So very simply, we talked about being at the end of the realm that this theory can actually explain, dot valence bond shell theory that we're working on. So we were able to draw a structure for sulfate ion that gave us zero, okay, formal charge for the sulfur when it has two double bonds. And of course, these singles get -1, and the oxygen is 0, okay? So this was the best structure, okay? Some people argue that, well, this structure here with one bond is more, I don't even have it here, but a structure with one bond is more realistic because it's sp3 hybridized, and sp3 hybridized can't have any unhybridized to allow pi bonding to occur. So the problem here is that if you follow your rules of formal charge, you may create atoms or molecule shapes that we can't explain. And again, that shows us that we're at the end of our theory of understanding, or at the limitations of this theory. So I'm asking you, imploring you to follow your rules, especially with elements that are beyond row 3 or 3 and below, 3 and beyond I should say, that have the D and can have expanded octets, but we don't have a good reason for how sulfur can double bond to oxygen. A lot of people don't even have this discussion with their students because it opens a door of we don't know, and we don't. And people will theorize that maybe the d orbital is helping this along. We're just not sure. One possibility is someone has looked at this structure and said that this is the structure for the sulfate ion, okay? And we notice that the structure will have a +2 for the sulfur and -1s for the oxygen, giving us an overall -2. And some people have suggested that this is the case because when they put this in a computer, they actually measured the sulfur to be 1.77-ish, not 2. Well, how did that happen? Well, we've theorized that possibly this +2 ion that's also doing a 1 covalent bond is pulling some electrons into the sulfur because it's so positively charged compared to the oxygen, creating the effect of double bonds that we come up with our formal charge rules. So again, all I'm asking you to do is come up with the best structure based on your rules, whether or not it makes something that we can explain. We're at the edge of this theory, okay, or at its limitations. So I'll never ask you, hey, what is the actual structure in real life? You would need experimental evidence. So very simply, if I'm asking you to draw, if you come up with this structure here, you'd have to draw 5 other structures to show where the double bonds are, okay, and alternate them, and to show resonance. You may say, Mr. Grotsky, there's no unhybridized P. How can there be resonance? We don't know for this structure. We just know that very simply that if I have double bonds on this side, why can't I have them here? Why can't the two double bonds be on this side? And you have to draw all those structures. And I believe there's 5 more if I was to ask for a test. Yes, we now know that this is probably the structure with the +2. Again, we're not sure. We can't look at these things. We can only hypothesize based on experimental evidence. You're not going to have that evidence. Okay, so let's go to SO3 and let's build the best structure possible with what we do know, okay? And that is just, we're loaded with formal charge information. So here we go. My S goes in the middle. I have my 3 O's. And I'll put up my valence electrons. 1, 2, 3, 4, 5, 6. Each oxygen has 1, 2, 3, 4, 5, 6. All right. And we have a structure that can't work. Sulfur has 6 valence. So the only thing we can do is we can create and move these 2 dots to create another bond. Okay, and now sulfur has 8, this oxygen has 8, and it looks to me like, wow, this is a really good structure. Okay, before we move forward, Let's do some formal charges. Okay, this oxygen is 0. This one's -1. And I'm going fast here because single bonded oxygens are -1. We've had plenty of experience. Let's figure out the sulfur. Half of its bonding and all of its lone pairs. It doesn't have any lone pairs, so it's half of its bonding. So if you notice, for sulfur, half of its bonding, it's 1, 2, 3, 4. 6 minus 4 is a +2. Red flag based on our rules. Red flag, that'd be +2. Now I know that's a red flag over here too. So we're following our rules. So we're going to do this again. Okay, so we're going to get rid of these charges. Okay, maybe. I'm trying to go backwards here. All right, now I am going to create another double bond. That double bond here would give me a 0 for, maybe, I'm getting a 0 here for this oxygen, right? Now it's half of its bonding and lone pair, 6 minus 6. This is still -1. Now this sulfur, let's check it out. Half of its bonding, there's no lone pairs. Oops. Okay, let's go back here. Okay, terribly drawn, but what I have here is 1, 2, 3, 4, 5. 6 minus 5 is -1. Okay, so that's a possibility. Is there a better structure? Well, of course there is. Can I make that sulfur 0? Can I get more zeros out of this? And you're right if you suggested, yes, you can. So take these two, okay, make these two dots, and you'll see that the oxygens are now all 0, okay, and the sulfur is sharing how many? Half of its bonding. Two, 4, 6. 6 minus 6 is sulfur 0. So based on formal charges, I get all zeros here. That means that there's less electrons being passed around that make this difference. So I'm going to draw myself sulfur, double bonded to an O, double bonded to an O, double bonded to an O. And this is, believe it or not, the accepted structure for sulfur, whether sulfur trioxide. It's not a polyatomic ion, there's no charge, and I get formal charges of 0. There's no resonance because it's all the same all the way around. I know it bugs some people. How in the world can something sp2 have a double bond in all directions? Because you only have one unhybridized p, how can you cause double bonds? Now you may say, oh, it has resonance. Well, if it has resonance, you'd have a double bond in one place. But there's no resonance here. It's the entire structure. Okay? And this, believe it or not, is the accepted structure, even though we can't explain how the world, one unhybridized p, can create 3 different, that's it, 3 different pi bonds. Can't explain it. We don't know. Is D's involved? Is there something else? Is there that idea of a positive ion creating that? Well, according to what we know, we're not really sure. Okay, there needs to be another theory to explain why, but you're able to draw it based on your rules. Okay, so let's do SO3 -2. I'll make some room for myself. Oh, by the way, this is going to be sp2 hybridized. Okay, 120-degree bond angles. Okay, trigonal planar, non-polar because it's very symmetrical. Okay, so let's do SO3 -2. Okay, and these are the advanced structures that you need formal charges to do, and they bother a lot of people because we don't have a good explanation to explain the structures they create. Okay, so here we go with the sulfur, and we have again the 3. Now you could draw a 3. I'm going to put them here because I kind of know what's coming. I have 1, 2, 3, 4, 5, 6. It's -2, so I'm going to gain 2. I'm just going to put them right in. Oxygen has 6, and here I go. It should be similar, but you notice it's going to have a little bit of difference. Okay, SO3, SO3 -2. Okay, so this sulfur is sharing 8, these oxygens are sharing 1. This could be a possibility. Let's check the formal charges. Okay, so this is -1. This single bonded oxygen, -1. This single bond oxygen, -1. Sulfur is, count all of its lone pairs. It's assigned electrons, half of its bonding. What do we get? 2, 3, 4, 5, 6 minus 5, valence electrons minus assigned, 6 minus 5, okay, is +1. Okay, now as you probably could guess, could I improve this? Well, absolutely. If I'm +1, adding another bond will make this 0 and make this go to 0. So let's do that. We're going to follow our rules. We have no experimental evidence to suggest it's anything other than following the rules that we learned. Okay? So let me do that. All right, and let's add some bonds here. Let's take these two. Let's add some black bonds. Okay, and we put them right here. All right, we're expanding the octet because now we have more than 8. But this oxygen becomes 0, and this. Okay, let's do this. Orange, half of the bonding, and its lone pair. Okay, which I missed. Oops. Okay, so 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. And what does that give us? That gives us a 0 here and a 0 here, and we have a -2. Notice the negatives on the more electronegative atom. This makes a lot of sense to me. So SO3 -2, the sulfite ion, okay, ite is for less oxygens. This right here is a sulfate. 8 is for more oxygens. Ite is for less. So sulfite ion, SO3 -2, is essentially going to look like this. We have an S double bonded to an O. We have a lone pair, single bonded to an O, single bonded to another O, and there it is. And as you probably can guess, this whole thing gets brackets, and it's -2 because it gained 2 from the environment. But we have to be careful. This thing has resonance. If I can write double bond on one side, who's to say they're not over here? So they can move around. We can't explain it because what's the hybridization here? Right, 1, 2, 3, 4, sp3. sp3 doesn't have any unhybrid orbitals, so we can't explain it. But we do know it does mix. So according to my rules, or we at least theorize it mixed based on our rules, okay? So we have to draw another one. I'll put the double bond over here, put the single bond here, okay, single bond over here, okay, -2, oops, sorry, and it's when I hit the pen a certain way it happens. And of course, the last structure is single bond to the O, and yes, you'll have to draw every one of the resonant structures if you think it does. Double bond here, since we didn't do that one. Notice on the double bond you have 2 pairs of electrons. Single bond O, and that's how you do SO3. So 4, 5, and 6 are bothersome in that we create scenarios that we can't or don't have the chemistry to explain yet based on these rules. Okay? And based on formal charge rules, this is what I expect you to be able to do. I can't expect you to explain why, because we don't know. A lot of chemistry teachers stay away from that discussion. I'm opening the door because I'm going to show you there's lots for us to understand. But valence bond shell theory that we've been on for the last 2 weeks has limitations. We have now reached it because electrons are not dots on a paper. They're actually waves and standing waves in areas. So of course we're going to run into limitations. Okay? So hope that helped. Take care.